A single honeybee produces approximately 1/12 of a teaspoon of honey in its entire lifetime. That jar of honey on your table represents the collective work of thousands of bees visiting over 2 million flowers and flying a combined distance equal to twice around the Earth. Honey is the only food produced by insects that humans consume, and it's also the only natural food that never spoils. Archaeologists have discovered 3,000-year-old honey in Egyptian tombs that remains perfectly edible today. Yet this golden liquid doesn't simply flow from flowers into jars. Instead, honey is created through an extraordinary biological and chemical process involving specialized bee anatomy, complex communication systems, and remarkable environmental engineering inside the hive. That spoonful of honey sweetening your tea required precise temperature control, enzymatic transformation, and dehydration techniques that would impress any food scientist. So how do honeybees transform watery flower nectar into the concentrated sweetness that has captivated humanity for millennia? Stay with me until the end, because what you're about to discover will change the way you look at every drop of honey, right here on Stories Behind Everything. Humans have harvested honey for at least 8,000 years, evidenced by cave paintings in Spain showing people collecting honey from wild bee colonies. Ancient Egyptians practiced beekeeping as early as 2400 BC, using clay cylinder hives and transporting them along the Nile to follow seasonal flower blooms. The ancient Greeks and Romans prized honey as food and medicine, with Hippocrates prescribing it for various ailments. For most of human history, honey was the primary sweetener available, far more common than sugar, which remained expensive and rare until the 18th century. Modern beekeeping began in the 1850s when Lorenzo Langstroth invented the movable frame hive, allowing beekeepers to inspect colonies and harvest honey without destroying the hive. Today, global honey production exceeds 1.8 million tons annually, with China producing nearly 30% of the world's honey, followed by Turkey, Argentina, and the United States. Everything begins with forager bees, female worker bees, typically 3 weeks old or older, venturing from the hive in search of nectar. A single hive contains 20,000 to 80,000 bees during peak season, with only about a third actively foraging at any time. Scout bees search for productive flower patches, and when one discovers a good source, it returns to the hive and performs a waggle dance, a figure-8 pattern that communicates the distance, direction, and quality of the food source to other foragers. The angle of the dance relative to the sun indicates direction, while the duration of the waggle indicates distance. This sophisticated communication system allows the colony to efficiently exploit the best available resources. When a forager bee lands on a flower, it uses its long straw-like tongue called a proboscis to suck up nectar from the flower's nectary glands. Nectar is primarily water, typically 70 to 80%, with dissolved sugars mainly sucrose, glucose, and fructose, making up most of the remaining content. The bee stores this nectar in a specialized organ called the honey stomach or crop, separate from its digestive stomach. A bee can carry about 40 milligrams of nectar, roughly half its body weight. While carrying this load, the bee can still fly, though it requires significantly more energy. During the flight back to the hive, enzymes in the honey stomach begin breaking down complex sugars into simpler sugars. The primary enzyme, invertase, splits sucrose molecules into glucose and fructose, beginning the transformation of nectar into honey. Upon returning to the hive, the forager bee doesn't directly deposit the nectar into storage cells. Instead, it passes the nectar to a house bee, a younger worker bee that remains in the hive. This transfer happens mouth to mouth, with the house bee extending its proboscis to receive the regurgitated nectar. This transfer serves multiple purposes. It allows forager bees to return quickly to the field for more nectar. It also enables further enzymatic processing as the nectar passes through additional bees. The house bee may pass the nectar to several other house bees in sequence, with each transfer adding more enzymes and continuing the chemical transformation. This process, called trophallaxis, also helps distribute pheromones and information throughout the colony. The house bees deposit the processed nectar into hexagonal wax cells within the honeycomb. However, at this stage, the nectar still contains far too much water to be stable honey. The critical next step is evaporation. Bees must reduce the water content from around 70% down to below 18% to prevent fermentation and spoilage. The colony accomplishes this through a combination of spreading the nectar in thin layers across many cells to increase surface area, and through intensive fanning. Thousands of worker bees position themselves throughout the hive and beat their wings rapidly, creating airflow that draws moisture out of the nectar and ventilates the hive. The fanning also helps maintain optimal hive temperature, typically around 95 degrees Fahrenheit, which accelerates evaporation. This dehydration process takes several days, during which house bees repeatedly visit cells, sampling the nectar's water content. When the moisture level drops sufficiently, typically below 18%, the nectar has transformed into honey. At this point, bees seal the cell with a thin wax cap, preserving the honey in an anaerobic environment that prevents fermentation. This capped honey can remain stable and edible for years, even decades, under proper conditions. The wax cappings are made from beeswax, another remarkable bee product secreted from special glands on the worker bee's abdomen. The composition of finished honey is primarily sugars, approximately 38% fructose, 31% glucose, and small amounts of other sugars including maltose and sucrose. The remaining content includes water at around 17%, plus trace amounts of vitamins, minerals, amino acids, enzymes, pollen, and various organic compounds. These trace components, though present in tiny quantities, contribute to honey's flavor, color, and antimicrobial properties. Different flower sources produce dramatically different honeys. Clover honey is light and mild. Buckwheat honey is dark and robust. Orange blossom honey has delicate citrus notes. Manuka honey from New Zealand tea trees has unique antibacterial properties. Over 300 distinct honeys have been identified based on floral source, each with characteristic flavor, color, and chemical profile. The antimicrobial properties of honey result from several factors. The high sugar concentration creates an osmotic environment hostile to bacteria. The low pH, typically between 3.5 and 4.5, inhibits many microorganisms. Honey naturally contains hydrogen peroxide, produced by the enzyme glucose oxidase when honey is diluted. Some honeys, particularly Manuka, contain additional antimicrobial compounds. These properties explain honey's historical use in wound treatment and its modern application in medical-grade honey dressings. Beekeepers harvest honey by removing frames filled with capped honeycomb from the hive. Modern Langstroth hives consist of stacked boxes called supers with removable frames inside. Beekeepers only harvest from honey supers, leaving sufficient stores in the brood chamber to sustain the colony through seasons when nectar is unavailable. Before harvesting, beekeepers use smoke to calm the bees. Smoke triggers a feeding response, causing bees to engorge on honey, which makes them less defensive. The beekeeper removes frames heavy with capped honey and transports them to an extraction facility. The extraction process begins with uncapping, removing the wax seals from the honeycomb cells. This is done using heated uncapping knives, or automated uncapping machines, that slice off the thin wax layer, exposing the honey inside. The uncapped frames are then placed in a centrifuge, a large drum that spins at high speed. Centrifugen schermerting schulteringen pleefchen, but the water quart amt dunks the welpuxerar, avissima hebben van die quarro verplaatboekdart, and komens the first are pure. The honey is then filtered to remove wax particles, pollen, and other debris. Most commercial honey undergoes fine filtering and sometimes heating to prevent crystallization and improve shelf appeal. However, excessive heating can destroy beneficial enzymes and diminish flavor, which is why many consumers prefer raw, unfiltered honey. After filtering, honey is stored in large tanks or directly bottled for sale. Honey's hygroscopic nature means it absorbs moisture from the air, so it must be stored in sealed containers. Most honey will eventually crystallize, forming sugar crystals that make it grainy and opaque. This is a natural process and doesn't indicate spoilage. The crystallization rate depends on the glucose to fructose ratio and storage temperature. Honey with more glucose crystallizes faster. Storage around 57 degrees Fahrenheit accelerates crystallization, while warmer or cooler storage slows it. Crystallized honey can be returned to liquid state by gentle heating, though excessive heat should be avoided. The work required for honey production is staggering. A single worker bee visits 50 to 100 flowers per foraging trip and makes multiple trips per day during peak season. Over its lifetime, a forager bee flies approximately 500 miles. To produce 1 pound of honey, bees collectively visit roughly 2 million flowers and fly about 55,000 miles. A productive hive might produce 60 to 100 pounds of surplus honey per year beyond what the colony needs for survival. However, bees don't make honey for humans. They make it as food reserves for winter or times when nectar is unavailable. Beekeeping is fundamentally about managing colonies in ways that encourage bees to produce more honey than they strictly need, while ensuring enough remains to sustain the colony. Honeybees face numerous threats that impact honey production and colony health. Varroa mites, parasitic mites that feed on bee larvae and adults, have devastated bee populations worldwide since spreading from Asia in the 19th. These mites weaken bees and transmit viruses. Colony collapse disorder, first identified in 2006, causes worker bees to abandon hives, leaving the queen and brood to die. Though the exact cause remains debated, factors include pesticides, particularly neonicotinoids, habitat loss, poor nutrition from agricultural monocultures, diseases, and possibly the combined stress of multiple factors. Beekeepers combat these challenges through integrated pest management, supplemental feeding, careful site selection, and sometimes moving hives to follow nectar flows. The pollination services bees provide while collecting nectar may be even more valuable than honey production. Approximately 1/3 of human food depends on pollination, and honeybees are the most important managed pollinators. In the United States alone, honeybee pollination contributes over $15 billion annually to agricultural production. Almonds, for example, depend entirely on bee pollination, and California's almond industry requires roughly 1.5 million bee colonies transported from across the country each spring. Many beekeepers earn more from pollination services than from honey sales. The processing and sale of honey involves quality considerations. Real honey should contain only honey, with no added sugars, corn syrup, or other additives. However, honey fraud remains a significant problem, with some commercial honey diluted with cheaper syrups or mislabeled regarding floral or geographic origin. Testing methods including pollen analysis, isotope ratio mass spectrometry, and nuclear magnetic resonance can detect adulteration, but enforcement remains challenging given the global honey trade's complexity. Different processing levels affect honey's properties and market value. Raw honey is extracted and strained but not heated or fine filtered, retaining all pollen, enzymes, and beneficial compounds. It often crystallizes and may appear cloudy. Filtered honey has been fine filtered to remove pollen and other particles, creating a clear appearance and slower crystallization but potentially removing beneficial components. Pasteurized honey has been heated to 161 degrees Fahrenheit or higher to kill yeast cells and prevent fermentation, but this destroys enzymes and may reduce health benefits. Creamed honey has been controlled crystallized to create a smooth, spreadable texture. Comb honey is sold still in the wax comb, the most natural form but inconvenient for some uses. The flavor complexity of honey rivals wine, with professional tasters identifying hundreds of distinct notes from floral to fruity, spicy to woody, depending on the floral source, regional terroir, and seasonal factors. Single flower or monofloral honeys come primarily from one plant species and command premium prices for their distinctive characteristics. Wildflower or polyfloral honeys combine nectars from various sources, creating complex flavor profiles that vary by season and location. The next time you drizzle honey into tea, or spread it on toast, remember the extraordinary journey it completed. Remember the forager bees visiting thousands of flowers, communicating through waggle dances, and carrying nectar equal to half their body weight. Remember the enzymatic transformations beginning in the honey's stomach and continuing through multiple bee transfers. Remember the house bees spreading nectar thin and fanning their wings thousands of times to evaporate water. Remember the precise moment when moisture drops below 18% and nectar becomes honey. Remember the wax capping that preserves it indefinitely. Remember the beekeeper's careful harvest and extraction. Honey doesn't simply exist as a natural sweetener. It's created through remarkable insect behavior, sophisticated hive engineering, and complex biochemical processes refined over millions of years of evolution. It represents one of nature's most perfect foods, and the collective effort of thousands of individual bees working in extraordinary coordination. And that spoonful of golden sweetness is a testament to the wonder of the natural world and humanity's ancient partnership with honeybees. Thank you for watching. If you have suggestions for our next video, feel free to share them in the comments below. We'll be sure to give you proper recognition for your contribution. Thank you for joining us on this exploration. Don't forget to like, subscribe, and stay tuned for more stories discovered through the smallest details.